In this video journal, we'll be discussing Experiment 4, Organometallic Reaction and Action, Parts 1 and 2. We began our experiment by obtaining the necessary equipment. It's important to note that for this experiment, all the materials and equipment must be completely free of water. The reaction vessel and diethyl ether solvent needed to be anhydrous due to the acid-base reaction that would occur between the Grignard reagent, phenylmagnesium bromide, and water. In the presence of water, phenylmagnesium bromide and water will react to form benzene, the unwanted byproduct. In the preparation of the Grignard reagent, bromobenzene reacted with magnesium iodine and diethyl ether to form phenylmagnesium bromide, the phenyl-Grignard reagent. In this reaction, magnesium performs a single electron transfer, adding into the C-Br bond attached to the benzene ring. During this experiment, when we added the spin vane, magnesium metal, and the crystal iodine to the 3 milliliter reaction vial and began to spin and heat it on the Corner stirrer hot plate with a heat setting of around 2 to 3 and a spin setting as high as it could go, we obtained a dark purple or violet color. In terms of isolating the desired product, we then added bromobenzene through the rubber septum around 6 to 8 drops at first to induce the formation of the Grignard reagent, and then added the rest of the bromobenzene. We then added the benzophenone dropwise. Finally, we added 3 molar HCl dropwise until 2 layers began to form. MgO was used in access, and the limiting reagent in this experiment was benzophenone. In the 1,2 nucleophilic addition to the ketone carbonyl of benzophenone to provide the magnesium alkoxide of triphenylmethanol, the phenylmagnesium bromide adds into the ketone carbonyl of the benzophenone. It then reacts with diethyl ether to create the magnesium alkoxide of the main product, triphenylmethanol. This is also known as triphenylmethanolate. After adding the benzophenone during the experiment, the color change observed was from a pale yellow color to a pink color, then to a yellow-brown color, and then back to the pale yellow. Furthermore, the rose-pink color lingered around the excess magnesium. The solid residue formed during the quench procedure. We broke it up using the closed end of a capillary tube, and the creation of the solid precipitate is not surprising because the 3 phenyl groups are extremely nonpolar, and this will be unable to be dissolved in the aqueous layer of the solution. 3 molar HCl was used for the workup procedure to quench the excess magnesium and to protonate the alkoxide salt, creating the triphenylmethanol. When a low pH was obtained by adding the 3 molar HCl acid, the color of the solution changed from pale yellow to bright pink, then back to the yellow color. This caused the solution to become acidic and form 2 distinct layers, the aqueous and organic layers. During the purification, we first obtained our culture tubes, which contained 2 layers. The top layer was a pale yellow color, while the bottom layer was a clear, cloudy white color. The top layer was the organic ether layer, while the bottom was the aqueous acidic layer. We then performed liquid-liquid extraction and dried the solution with anhydrous sodium sulfate, and performed thin layer chromatography of biphenyl, benzophenone, triphenylmethanol, and the final lane was reserved for our own ether solution. We boiled off the ether of our solution, leaving us with a small amount of pale yellow product in the culture tube. We weighed this because it was our own crude product. We then began recrystallization by adding methanol, placing it in the hot water bath until it was completely dissolved. After that, we placed the solution in an ice water bath. Once the solid precipitate was formed, we vacuum filtered the solid crystals, and this became our purified product. In terms of the RF values, for biphenyl, I got 0.94. For benzophenone, I got 0.83. And for the triphenylmethanol, I got 0.91. And finally, for our own ether solution, I got 0.93.